Yeah. That one is due the 22nd, so next Monday. Yeah.
Okay, so I'm not saying that it was due Friday, but is that Monday?
Yeah, I'm pushing it. I was gonna have you guys turn in a little early so I could look over them. I'm gonna assume that you are a masters and know your stuff. Like we can just review them on Monday together. Okay, so you know where all the metals are on the periodic table. Where are they generally? So what percentage of the periodic table do you think are metals? 80, 75 to 80%. And I'm going to turn this periodic table around today sometime. But where the little metalloid line is, to the left are all the metals. Non-metals are up in the upper corner. Some of the properties you usually have some not common sense, some background knowledge on. But some of the other ones are going to be things like number of electrons that they have in their valence shell. Number of electrons meaning like the reactivity of them, if they're going to gain or lose electrons. Some of that background knowledge is going to be related to their chemical properties, and then I'm going to come down here in just a second to physical. So 3 of the most important things to know for metals are that they have few valence electrons. VE, valence electrons is what that means. So they're really going to be likely to lose electrons. Why does this matter? Who heard the word octet or learned a little bit about octet in the video? Octet meaning 8 electrons in their outer shell. Okay, we're going to get to that in a second. Octet is a happy atom, okay? And happy atom has 8 electrons in its valence shell. And we're going to get into valence electrons in just a second. And so what's easier, if you have 1 or 2 electrons, are you going to gain 6 or 7? Are you going to lose those 2? Because actually, if you lose electrons, you might back up to 8 electrons, which is an inner shell. And so there's some images I'll show you. They're concentric rings, and the last shell that was filled does have 8 electrons in it. So you can, for example, if you're a metal, you can lose relatively few electrons and back it up to a previous octet state, which is favorable, which is great. So they're likely to lose their electrons, and a lot of times they are basic. Basic meaning pH above 7. The other ones we'll get to shortly. Nonmetals, they're going to have more valence electrons. So instead of gaining electrons, instead of losing electrons, they're going to gain to reach 8 valence electrons. That's very common. So both of these sides of the coin mean that these things are very reactive to an extent. There's an extent of reactivity based on the number of electrons they'll gain or lose. Second is that they contrast. They're going to be mainly acidic in their oxides or their aqueous forms. Physical properties, these are ones you're probably more familiar with. Conductors, so metals are going to be conductors, not only conductors of electricity, but of also heat. Malleable, ductile, lustrous. I'll kind of circle the keywords, because some of these definitions you might actually know. Luster, and solid at room temperature. Those are the ones that I think, who feels like pretty familiar with those? The ones that you've gone over before. Okay, great. Characteristics of nonmetals. So they're pretty much opposite on almost every account. So they are not great conductors. They're poor conductors of heat and electricity. This one's weird. Brittle just means that it cleaves really easily. So think of a big loaf of bread. Cleaving would be like slicing off a little bit at a time, meaning it's easily done like that. Non-ductile, so it's not going to be able to be pulled into a wire. Usually their gases or liquids at room temperature. There's one solid, and it's solid iodine, and there's another liquid, which is bromine liquid. Everything else is usually actually a gas. I'd say 9 out of 10 of the nonmetals are gases. So this is some review material. And then, we're going to take a couple more notes, and then you guys are going to pull out one of your periodic tables. We're going to work on electron configuration patterns. Okay? So if you don't remember that stuff, it's fine. first want you to do before we jump into the electron configurations and meaning on your blank periodic table, I have some, I'll let you grab some coloring equals or anything like that in a second. On your blank periodic table, everybody have one, at least one. If you don't have one, okay? You should have it from your very first stakeholder. You're going to go through and label from the periodic table the blocks that are S, P, D, and F block. And you can totally ask a friend, because from the video, I think it looks like about 78% of us watched that. So label S, P, D, and F block on your periodic table. You can shade them all a different color. That's totally fine. And then each of the groups that end in these 4 electron configurations. So if they end in S2, end in D10, P6, and F14, I want you to just color code. So, yeah. Yeah. So that's what you're going to do first. And then after that, I want you to look and think about this question highlighted in highlighter. And then after that, you guys will start the bottom piece. So I'm going to say take less than, I don't know, 8 minutes or so to get this first 2 parts done. Who feels comfortable doing this based off the video? You know where these things are. Okay. Then help each other out. You need to pull up the video, pull it up now. So just kind of lightly color them. It's easier for your brain to remember things in color than in black and white. They can't differentiate sometimes. So it's good to try to use some color there. You can even pull up images up here on table if that's helpful. Okie dokie. So on the highlighted question up here, first of all, our big main question is basically how our electrons are arranged around the nucleus. We know that they are actually put onto the atom in layers by layers by layers by layers, like an onion. The electrons that are closest to the nucleus are very, very tightly held to the nucleus. The electrons that are farther away are loosely held to the nucleus. So I think of a teenager child near mom, very low energy, chilling by the nucleus, well behaved. Far away from the nucleus, not near mom, high energy, less well behaved. So that's kind of our goal, is to start thinking about how these electrons act, but we first have to figure out where they live and what they do when they're close to the nucleus. So as you're looking through the groups, point to me, are groups this way or this way? Groups are this way. Those groups I told you to identify were groups that ended in S2, D10, P6, and F14. So what are we clear on now? Can you make a statement about the electron configurations of each of the representative groups? Each of the groups. Can I get somebody to finish that statement? Each of the groups end in the same electron configuration. That's it. So every group ends in the same electron configuration. That's going to give us a lot of insight into how each of these things are grouped together and why they're grouped together the way they are. So this group electron configuration that Matt just kind of told us about, that is literally what electron configurations are supposed to show us. That there is something called a pattern, periodicity, to be specific, that exists as we go across the periodic table. So every time I get to the second group, I'm going to be saying S2. Every time I get to whatever group this is with zinc, I'm going to be saying D10, and then P6 and F14. But of course, in the middle, I'm going to be saying other things. Like, for example, I'm going to be saying when I get to manganese, for example, blah, 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 and I'll say 3D5 because I'm at the 5th electron over in D block. But everything here in manganese's group will have the same ending point of D5. It's just the number in the front is going to differ because we're doing it based on different periods on the periodic table. So the periodic law is that there exist patterns, repeated patterns, across the PTOE. That's it. And as we go across the periodic table, we're going to see those. Basically, they're correlated with the electron configurations. And so another word to say that they're saying something about the periodic law is to call it periodicity. So where did they come up with this whole word, the periodic table, from? It's a table that has periodicity. It has repeated patterns throughout it. That's where the whole the word periodic came about, or at least to describe this table. So let's look into a little bit more, depth about the electron configuration. So this is something you should be able to do, and if you've not watched the video, watch it during teal. I want you to write out the longhand, the shorthand, orbital diagrams for each of these. So let's kind of look at one by one. Neon, find neon. How many electrons does it have? Neon has how many? 10 electrons. Give me a thumbs up, you know how to find it? Because you can look at the atomic number. There are 10 electrons that must be accounted for in neon's atomic structure. So neon's going to start off, and you guys have a periodic table in front of you. I don't. We're going to start off by going through the 1s electrons. And we're going to build, so that's 1s. We're going to build here. What is this one called? 2s. Where is the 2 coming from? Second period. And then we're going to get over here and go through what? 2p, because we're still in the second period, but now we're not in S block, we're in P block. But every electron, every element I go through is adding an extra electron. I must account for all of them. So it's going to go 1s, how many? 2, because that's going through helium, hydrogen, helium. Helium actually belongs here. It's a small atom with hydrogen. Then we're going to go through 2s, 2, and that takes me through, ooh, my bad. That takes me through beryllium, and then I'm going to go from 2p all the way over to the end. How many electrons am I counting for over here? 6. 1, 2, 3, 4, 5, 6. That's it. That's how electron configurations work. You build the atom. When we get down to D block, we will have to make one more note about how these electrons build. So that's 2p6. What you should be able to tell me are that each of these big coefficients are energy levels. You go with that? Energy levels, periods, principal quantum number. There's another name. Orbitals. The second letter is the type of orbital that it exists in. So these are the things I'm saying. The 1, for example, is an energy level. The S or P is the sublevel, and this is some terminology you'll see on your PS5, okay? So the sublevel shape of the orbital. And those shapes come in some funky looking shapes. They look like spheres, which the S's look like. The P orbitals have a dumbbell shape, like this. They come in 3 different orientations. P like this, P sideways, and then P that goes into the board, and then comes like out of the board. Guess what these orientations are if you're thinking about like an axis. What's an axis that goes this way? This way? X-axis. So that's sometimes referred to as PX. What's one that goes this way? PY. And in and out? Z-axis. You know what the Z-axis, it's like makes everything 3D. All right, well, you learned that today, okay? So the Z-axis. So what's nice is that there are 3 p orbitals. From your recollection of the video, how many electrons go into each orbital? 2. Good. 2 electrons in each orbital. So if I have the s orbital, I have 1 of them. So here's how you draw. I'm going to actually draw the orbital diagram with you guys here. So you draw a line to represent the orbital. You label it 1s to say it's the 1s orbital. This one actually does have 2 electrons in it. How do they spin? Opposites of one another. So one goes up and one goes down. Okay, that's taking care of 2 electrons. The second orbital, very similar, but it's a bigger orbital because it's the second energy level, but it's still 1 orbital. It's the S sublevel, and it has 2 electrons in it. One that goes up and one that goes down. Why are they spinning opposite? Any idea? Right. Electrons and electrons, they repel each other. They do not like to be near each other. So if they spin opposite, it helps them feel less repulsion, and they can kind of coexist together in that same small orbital. The orbital looks like in a sphere for the s orbitals. Now we're getting to the p orbitals. You'll notice I have 6 total electrons in this one. How many orbitals are in the in the p sublevel? 3. 1, 2, 3. I've actually drawn them for you here. So to indicate, instead of drawing these funky things, we just draw them like dashes. 1, 2, 3. And then we actually label them all 2p, so we're clear that these represent the 3 p orbitals. Everybody should be writing this down, especially if you didn't write or watch the video, because you're not going to have any background knowledge to do your homework. So make sure you're writing down additional notes too. Okay, so then these have to be filled a very specific way. They're in accordance with Hun's rule, off-ball, so awfully low, and Pauli exclusion principle, meaning the Pauli pair rule. They get filled one at a time. That's what Hun's rule represents. One goes up, that's in that one. I don't want to double up now because there's a repulsion of electrons. So then I have to fill this one. These are my lazy arrows. They're just like half arrows. And then this is the third one. So far I've got 3 electrons in the 2p sublevel. Now I can actually go and fulfill all the way up to 6 because now I have no choice. I must double up. I must fill them. So this is the Hun's rule. Fill one at a time. And then the Pauli rule means you can pair them up, maximum of 2, opposite spin. And so this actually is a full electron orbital diagram with how many electrons? 10. You can see 10 of them doubled up here. And you can count up 2 plus 2 plus 6 equals 10. And I just like to remind you of that because we actually said very beginning that neon should have 10 electrons. But now we know where they are. They exist in these orbitals that are shaped like this. Second, you can write actually these longhand versions of electron configuration in a much shorter way. It's called the noble gas shortcut. Where are the noble gases on the periodic table? Far right, so group 8. That neon is a noble gas. So I'm okay if I do say noble gas electron configuration. You can just put neon like this, which is really easy. That's just simply because it is itself a noble gas. But the better way to write it would be like, what's the last noble gas that neon that happened before neon? Helium. And this one's not all that helpful because you're not really cutting out too much. You're cutting out 1s2, that's it. But once you have bracketed helium, that means everything up to helium's been taken care of, and then you continue. So I want you to continue. 2s2, 2p6. Okay, I like writing in this way because it shows you what the valence electrons are. So the valence electrons, here's a definition for you, okay? Valence electrons. I'm like teaching, taking notes, and doing examples all here. Valence electrons are electrons in very outside energy level. That's as simple as I can make it. And we're going to talk a lot more about what they do, but this is how you can identify them. So V for valence and very outside should kind of stand out to you. And when you're looking at the energy levels in neon, what energy levels do you see? Energy level, which ones do you see, Melanie? But what are they? Energy level 1, right? And energy level 2. So energy level 2 is the highest one we've reached because you don't see anything past that. How many electrons are in the second energy level? 8. These 8 right here. 2 plus 2 is 8. Look, and then if you look up here, you can see them very clearly. 2 plus 6 is 8. 2 plus 6 is 8. 2 plus 2 is not 8. Okay, so the valence electrons are just simply where the outer shell is, so the outer shell being the valence shell, and you count the electrons in it. That's it. Okay, so let's do another one. Let's do barium, and I'll come back to chlorine because I'm taking space. All right, so barium. Find barium and tell me how many electrons it has. How many? 56. Whew. All right, let's get going then. So, start me off at the beginning. I'm asking you to look at your periodic table, okay? 1. Okay, chant with me. 1s2. 2s2. 2p6. Where are we at right now? But where are we? We're at neon, right? Okay, now we jump down to 3s2. Good. 3p6. And who are we at now? argon, right. So we've gone all the way through 1s2, 2s2, 3s2, 3p6. We're at argon. Now we're going to get down here, right? Okay, keep going. 4s2. Good. So right here is where you're in the fourth energy level. But D block is weird. D block energy levels are of lower energy. And so they actually drop down in energy level. So instead of going straight to 4D, you go 3D. How many? 10. So I'm going to show you everybody that on the periodic table real fast. So we've gone through 3s2, 3p6, 4s2, and then when you get here, you might as well write this down if you don't have it already, on your colorful periodic table you just created. When you get to the to D block, do n minus 1. N is the period number. N is the period number. And so that's when instead of us saying 4D10, we're saying 3D10. That's only for D block though. So then where do you pick up when you get back to P block? Pick back up at 4. Good. 4P6 to be specific because you're going across 1, 2, 3, 4, 5, 6. Okay. So we're almost there. Okay. So what's after 4s2, 3D10, 4P6, 5s2. Good. And the 10 is representing the 10 electrons across. So oops, 4D10. And then, good, 5P6 to jump back to the fifth energy level. Whew, finally, we're down there. The barium, 6s2. So on yours, you guys have 3D10. Let me catch up with you fast. 4P6, 5s2, 4, I'm sorry. Yeah, that's right, 4D10, 5P. Sometimes my brain goes faster. And then, thank you, 6 is this again? 6s2. Okay. If I had to count up all these exponents, how many would there be? 56. There should be because they should match the number of electrons here. Okay, shorthand means go back to your last noble gas. Who is it? Xenon. And where does that end? What's the ending point for xenon? 5s6, right? I mean 5p6. That's this right here. Everything in brackets, all that is xenon, right? You with me? So instead of writing all that crap, just go xenon. 6s2, just to finish off the last bit, that gets you to barium. So that's only acceptable when I say shorthand or noble gas shortcut. If I say longhand, I want longhand. This is shorthand. Second, I want you guys to tell me how many valence electrons are here. Second, where are the valence electrons? What energy level are the valence electrons in? They're in the sixth energy level. How many electrons are in that level? 2. 2 valence electrons. And you can actually tell that straight from here. That's the sixth energy level. These are the 2 electrons in it. Now, if you wrote up the longhand, basically you'd look for the last thing you wrote and say how many total are here. There are 2 electrons. So the two valence electrons are what you should denote from that. Orbital diagram. Let's draw a part of this because I want you comfortable with the D block ones. So let's just kind of isolate a small section of this. Actually, no. Let's do the orbital diagram for iron. Ready? Electron configuration of iron. Electron configuration first. Iron's in the middle of D block. So starting off, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. How many? How many over is iron? Count again. 1, 2, 3, 4, 5, 6. Does everybody see the iron is 6 over in D block? Yes. Okay. Then you write 6 here instead of 10. Most of the time we're going to the end of a block unless we're getting stuck in the middle. So how many electrons are here? 10, 16. Is there 16? I mean 26. Sorry, 26. There we go. Okay. Orbital diagrams. Here we go. 1s. What do I draw there? Up and down. 2 electrons. 2s. What do I draw? Up and down. 2p. What do I draw? 3. What are the lines representing again? orbitals, but they're 3 orbitals that are of different orientations. Good. And you fill them how? Oh, hold on. Say again. One at a time, and then double them up. And I have you do this even on your own because I don't want you to get mistaken, actually practice it wrong because you'll get in a place where you may not have them all filled, like the end here. Okay, 3s2 up and down, 3p. Again, there's 3 orbitals in the p sublevel. And then up, 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 down, down, down. Okay, almost there, guys. 4s. How many electrons? 2 electrons. 3d. This is the one I really wanted to get to. How many orbitals are there? There are 5 orbitals. These are standard numbers. In the s, there's 1 s orbital. There are 3 p orbitals. Can you tell me what the trend is here? Up by 2 each time. Good. 5 d orbitals and how many f orbitals? 7 f orbitals. It is up by 2 each time. So you can memorize that. But I do think it's helpful to put the brackets because I help you identify. So I have to draw 5 d orbitals. 1, 2, 3, 4, 5. These are called 3d. I'm running out of space. There we go. Now, how do I fill these? How many electrons actually are in all of these? Well, there's up to 2 in each one, but there's 6 electrons that are actually have to be accounted for, right? So how do I fill them in here? One at a time first. So Hans 1 rule, 1, 2, 3, 4, 5. And then one of them gets a buddy. Okay. So if you did not fill it one at a time, you would have put 2, 2, 2, and then had 2 unfilled orbitals, and that would have been incorrect. So there must be 1, 1, 1, I'm sorry, 5 ones at the 6th one. So then I can ask you, how many are unpaired? How many electrons are unpaired? 4 of them are unpaired. So that would be an easy question to get wrong if you didn't have the appropriate destination. And then I think that's, oh no, how many valence electrons are in iron? Okay, let's go back. What is the valence shell? What is the valence energy level? 4. You see it goes 1, 2, 3, 4, 3. 4 is still the highest energy level. How many electrons are there? 2. So iron, in this example, has 2 valence electrons. Simply because the 4th energy level has 2 in it. Right, who's feeling a little bit better? Like on a scale of 1 to 10. 10 means you're pretty awesome. 1's like, what the heck are you doing? Am I in chemistry? Yes, you're in chemistry. Okay. Let's do an ion one then, and then I think that'll help us with our electron configuration. You guys want to do phosphorus or tin? Phosphorus, because it's got less electrons. I like it. Okay, so let's do this guy. Phosphorus 3 minus. How many electrons does phosphorus 3 minus? Say again? 18, good. So phosphorus itself has 15 electrons. But since you have a 3 negative charge, you must say there are 3 more electrons. So that gives us a total of 18 electrons to account for here. Okay? So then start me off. 1s2, 2s2, 2p6. You're going to start like dreaming of this. 3s2, 3p6. Okay, I'll start off with just normal phosphorus, and I'll come back to the ion. So if you count this up, that should be 10, 5. Okay, so that's 15 electrons right now. That's phosphorus on the dot on the periodic table. How many valence electrons does phosphorus have? How many valence electrons does phosphorus have? 5. 5. So these are the 3rd energy level. And if you count up 2 plus 3, there are 5 valence electrons. What is the goal of all atoms? To have how many? 8, which we call an octet, right? So if I were phosphorus, how many electrons, or what would I want to do? Would I want to lose all 5 electrons or gain 3? Gain 3, why? It's closer, I have very little energy put forth to this. Okay, so it's going to gain 3 electrons to make octet, which is this happy place, okay? Everyone wants to be like the cool kids, the noble gases. So how does it add 3? where does it add? Where does it have space? In the p, in the 3p orbital. It has space for 3 more electrons. So instead of ending like that, it's going to end at 3s2, 3p6. And who does that look like? Whose actual electron configuration is that? Argon. So just like I said, everybody's goal is to look like the cool kids, the noble gases. So every single time you make a charge, it's not willy-nilly, hey, like I think I want 1 electron. It has a purpose. Its purpose is to have the electron configuration of that of a noble gas. Noble gases are the ones that are most stable. So 8 valence electrons means that you're very stable and happy again. Okay, I generally say happy because I want you to just kind of understand the concept, but it's more about the stability of the atom and how the electrons interact. But if it looks like this, you can tell that it's got 8 electrons. It looks like argon. But we know it's still phosphorus. Why is it still phosphorus and not argon? Because protons never change. The protons are the identity that was 15 electrons. I mean, protons, which is still controlling its identity. Okay? So that's how the electron configurations of an ion are slightly different. Okay. Whew. This is the valence. I have a little bit more with you. The valence stuff, you write down what you need to. I think that there's a lot of reading. I'm a talker. How to figure that out. But the parts here I want you to summarize are, we already talked about this. This is another fun fact. They are the ones that are most reactive. It is the valence electrons that are gained or lost. Summarize that someplace on your notes. The inner electrons, they don't play. They stay locked in the core. The third bullet point here is something you've probably already written down in a different way. On the very first periodic table that you colored, you wrote down some facts about the groups, like alkaline earth, alkaline metals, halogens, and those were properties of that group. But now we know that those groups have the same valence numbers. So basically this means same valence electrons means same properties. Because all properties stem from simply the atom trying to get octet or to give somebody else octet. So it's going to react by either giving away 1 electron, which is really easy, so it's usually very, very viciously reacting, or it can gain or lose an electron that way, which is going to be high reactivity. Or sometimes it's going to in the middle. Maybe it's got 4 valence electrons. It's going to be hard to get octet either way. So sometimes those are not very reactive because it's just not very easy for it to get octet. So those valence electrons really do control the chemical properties, specifically chemical properties, not the physical properties. It's more about the chemical properties, about reactions, about reactivity. And then the group number on PTOE, this is how you can tell the valence number very quickly on your little towers. Okay, this is group 1A. That's close. This is 1 electron, 2 electrons, valence electrons, 3, 4, 5, 6, 7, 8. Those are the valence electrons. They are based on their A group numbers, group like 1A through 8A. Okay. I have a little bit more to tell you on some introduction to properties of periodic table some more. But I want you guys to start this first part without me, and then you just have to turn your attention back so that we can finish up together. So this is yours again. It says do not write on lies. Playground, this is yours. I copied these freshly for you guys. Okay. So I want you guys to do with somebody next to you. You write on it. After doing a little little bit of reading at the top. Somebody next to you, I want you guys to do 1 through 4. And then on number 5, it talks about coulombic attraction. Let me talk about coulombic attraction in about 5 to 10 minutes, okay? So 1 through 4 right now. I will put it up on the board too. You can see the copier, it hates me because there's all this empty space for some unknown reason. I'll put the questions up there like that if that helps. What is a radius? So halfway across the diameter, so we have an atom, so half the atom. Right? Okay, so basically, it's how big the thing is. That's it. That's how big it is. Why does something get bigger? Can you see the diagrams as you go down? What are those rings representing? Thank you. Energy levels. Okay, so this is where all the aha moments are coming, okay? Staying with me. Look, we have one energy level. OMG, we have a second energy level. It got bigger. It got bigger. It got bigger. It got bigger. What energy level am I at? Energy level 5. This is N equals 5. Okay, this is kind of related almost back to the Bohr model, at least the concentric rings. As energy levels increase, the radius increases. Okay, so are we okay with that logic? That's easy. The one that's a group trend. Right, and that was what we talked about going down a group. Now across the period, what's happening to the energy levels? So hold on, leave it like that. Nothing is happening to the energy levels. Great, guys. Okay, so on the period, nothing is going, like the energy level is like energy level, what is this, lithium? This is energy level 2. But the energy level is not affecting the radius, right? But the radius is going down across, that way, across the group, right? Why would that be? What are the things that are in the energy levels? What's subatomic particle? What subatomic particles are on the outside of the nucleus? Electrons, and they're negatively charged, yes? Okay. Well, the nucleus is positively charged, yes. What do they do with each other? Opposites attract, right? Positively charged protons love their electrons. So I always think of the nucleus as mom nucleus. Electrons are crazy adolescents. They're on the outside. So this nucleus is weak. It's letting the outside stay pretty far away from it. This nucleus, what would you say it would be? Stronger, because what is it doing to its rings on the outside? Sucking them in, saying, no, you cannot go out to the party or anywhere else. Okay, that's what this is. Why is this nucleus stronger? It has more protons. How many protons does lithium have, guys? 3. How many does neon have? 10. So we have a name for this. It's got a whole little phrasing to it. It's called the nuclear effective charge. The effectiveness of the charge of the nucleus. Doesn't that make sense? If the nucleus is very effective, it attracts its rings, its energy levels, and sucks them in because it's attractive. That's because it's got a strong charge. It's got a lot of protons. If the nucleus is weakly attractive or weakly effective, it doesn't do that. It leaves its electrons hanging out, and so the energy levels are farther away from the nucleus, so its radius is what? Bigger, right? Its radius is bigger. Okay, so you kind of have come to some of those conclusions. Let me give you a little bit of some verbiage here so that you can study these. You will have to explain these two trends, or these two factors, on your explanation part of your proof. You know how I had one on last time? You'll have another one here. So we're going to talk about the 4 trends. Actually, we'll talk about like 1 or 2 of them today. But these factors that affect the trends across the periodic table exist for every single trend. So the effective nuclear charge is a period. It's a period factor. And that's because I only use that term or that reasoning to explain something when I'm talking about a trend across a period. And don't forget, a period is left and right. And so since we're talking about the same energy level, it's not the energy levels that are causing the radius to change, it's something else. It's the protons. So I want you to fill in the gap here. So more protons per energy level means a stronger pull, which does what to the radius? Smaller, right? I'm going to say decreases the radius. And that's just simply because attractive forces are in effect, okay? And attractive forces is kind of what Coulombic attraction is. I have that at the bottom here. So the shielding effect is the name that we give to the effect that we already talked about. The energy levels building, causing the radius to increase. There's a little bit more to it, though. Something about this word shielding has to be noted down here. So what we talk about is the fact that nucleus is going to be positively charged. This nucleus is positively charged. But that attraction for its electrons can be shielded by other electrons. So if we're talking about a small atom with one energy level, there's no shielding because there's nothing between mama nucleus and adolescent electron, right? There's nothing between them to eliminate the attractive forces there. And so that's going to have a a very small shielding effect, or small shielding. And if we have something that's lots of energy levels, let's say 5 or 6, and the electron's out here, that's our valence electron, don't forget it's on the very outside, there's a large amount of shielding. There's negative, 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 negative. There's all these negatives in between. And that distance makes a difference in the attractiveness between nucleus and that valence electron, outside electron. So this would be lots of shielding. Okay, so this is where I want your comments here, okay? Which valence electron? Valence electron over here in the lots of shielding case, or the valence electron here in the low shielding case? Which do you think is more freely able to leave, to be knocked out, to be used up in maybe a reaction or something? The left or right? Left. Why? Okay, so there's very little, what's the word? Attraction for the positively charged nucleus. So this one has low attraction, so high reactivity. Simply because it's farther away from the nucleus. The nucleus has no lock on it, no attraction to it. So that electron's going to go off and do its own thing. Usually, in a reaction, it's able to really freely come off. That's going to be very important in some of our later trends we talk about. The atomic radius one is the easiest one, because you can see and understand the radius much easier than the other ones. So the last little part is Coulombic attraction, and it takes together the two factors we just talked about, mainly about attractive forces. But it helps you to kind of put a name to what we're talking about. Sometimes it's easy to have a phrase to identify with versus a big long explanation. So Coulombic attraction is the force of attraction that two things feel for one another, or the force of repulsion two things feel for one another. And so this whole phrase, the greater the distance The heart does not grow fonder, okay? Distance does not make the heart grow fonder. It is just not there. The attraction is very low. Because it's so far away, the electron has no attraction for its own nucleus, which makes it very reactive. Well, that's also going to be, that's a positive, let's see, nucleus, that's a positive negative attraction because the opposites attract there. The other force that could be at play could be a force of repulsion. Maybe this is something you feel about somebody else. I don't know. So, for example, electrons and electrons, they do not like to be near each other. So that actually, two electrons against each other would be repulsive, which means that it's unstable. It's a very high stress situation for an atom. I know we're talking about atoms and their feelings, but it's a high stress situation for them. And so the lesser distance, so the closer they are, the even more repulsive. And so that's why I have distance on the bottom here, because it's an inverse relationship. So the force is stronger when the distance is smaller, inverse relationship. Increased force with decreased distance. But the two, I think, that are more important are the shielding effect and nuclear effective charge. But the Coulombic attraction talks about factors of this. Okay. All right, so I think that allows you to finish up some more on that total sheet you're working on right now. I want you to look specifically putting down some ones, because they're going to introduce you to the other factors or trends on the periodic table, and those are going to be talked about probably more tomorrow. I'll try to stop now. I've killed you today. But just keep working with the partner on that, and I'll try to